Flipped classroom video for Maths A2 Unit 3, Proof by Contradiction. The first one we're going to look at is a modulus inequality, and this is a particularly beautiful proof, I think. The theorem is that the radius to the point at which a tangent touches a circle is perpendicular to the tangent. So here we have our circle and the tangent marked with a red T and the radius from O to B. Now the logic of contradiction we're going to follow through as we look at this. So the first thing is that we assume the opposite of what we're trying to prove. So in this case the opposite of what we're trying to prove is that OB is not at right angles to T. We're trying to prove that OB is at right angles to T, so the opposite is that it isn't, and that symbol there is a right angle symbol with a line through it that means not. So OB not at right angles to T. And there's a few of the symbols we're going to use. We've got a backward capital E, which means there exists or there is. That slash means not, so if you slash through another symbol it means the opposite. ST is such that, and then that hash sign is contradiction. And we will come to that in a bit. So we assume the opposite of what we're trying to prove. Then we take some logically correct steps. So let's have a look. If it's true that OB is not perpendicular to T, then there must be some other line from O that is perpendicular to the tangent. So that means there must be a point on the tangent such that the line from the centre of the circle to that point is at right angles to the tangent. Now this looks a bit odd on the drawing, and that is because it isn't actually true, but remember we're assuming the opposite of what we're trying to prove, and so it might look a bit odd on the diagram. Now, following on logically, so logically correct steps. Since triangle OBC has a total of 180 degrees, as all triangles do, and we already have a 90-degree angle at C, then we can conclude that the angle at B must be less than 90. The angle at B plus the angle at O must be 90, therefore the angle at B must be less than 90. Now, since OCB is 90 degrees, then because we've shown that OBC must be less than 90, that tells us that OBC must be less than OCB. And since the side opposite to a large angle in a triangle is longer than that opposite to a smaller angle, we can conclude that the side opposite to OBC, which is OC, must be less than the side opposite to OCB, which is OB, and that means this has led us to an incorrect conclusion, because OC is not less than OB, because OC is greater than radius. It goes from the centre to outside the circle. That means OC must be bigger than OB, and this conclusion contradicts a known fact, and that means that the original assumption also does and must be false. And if the original assumption is false, that means the opposite of the original assumption, i.e. the theorem, must be true. So that means the radius to the point at which a tangent touches a circle is indeed perpendicular to the tangent. So in symbolic form we've got there, therefore OB is perpendicular to T, the tangent. Now the irrationality of root 2. Theorem. Root 2 is not a member of Q. Now little e means a member of, so a slash through it means is not a member of, and Q is the set of rational numbers. So we are saying that root 2 is not rational. Now there's a very interesting history behind this which you could look up, but we're going to just go for the proof today. So the other way of putting it is we can say the square root of 2 is irrational. If it's not a member of the rational numbers, then it is irrational. Okay, so we'll have the logic of contradiction going down the right hand side again, and the first thing is we assume the opposite of what we're trying to prove. So we're trying to prove that root 2 is not a member of Q, and so we assume that root 2 is a member of Q. Then we do our logically correct steps. So the first thing we do is, if root 2 is a member of Q, then it can be expressed as a fraction, a over b, where a and b are in Z, which is the set of integers, and the bracket a comma b is 1. And what these things mean, so I've just said Z is the set of integers, brackets a comma b means the highest common factor of a and b. So the fact that we've stipulated that the highest common factor of a and b is 1, what that means is it can't be cancelled any further. So this is a fully cancelled down fraction. We'll come to 2z in a minute. That is the set of even integers. Now, if root 2 is equal to a over b, we can square both sides. So we have 2 is equal to a squared over b squared. And that means that 2b squared equals a squared. Now, since a squared is 2 times another integer, then a squared must be in the set of even numbers. And that means that a itself is a member of the even numbers. When we square an even number, we get an even number. When we square an odd number, we get an odd number. Therefore, if a number squared is even, then the number itself is even. So, more logically correct steps. Now, this means if a is an even number, then a must be able to be expressed as 2 times another number c, which is an integer. C is a member of Z. And we can then square a, which gives us 4c squared, and we know from above that a squared is equal to 2b squared, so that means that 4c squared is also equal to 2b squared. And now we're going to get to our contradictory conclusion. If we divide both sides of 2b squared equals 4c squared, that gives us b squared equals 2c squared. And that tells us that b squared is an even number, and that tells us that b is an even number. But this conclusion contradicts a previous part of the argument, and therefore the original assumption does and must be false. What does it contradict? Well, we've discovered that a is an even number and b is an even number, but right up the top there we said that a and b were co-prime, or another way of putting it is that a and b had a highest common factor of 1. Now if a is even and b is even, then they have a common factor of 2. So there's a contradiction there, and that means that our original assumption that root 2 was a member of Q must have been false, because all the steps we've taken are correct. And we therefore have a contradiction, and that means that the opposite of the original assumption, so the opposite of root 2 being a member of the rational numbers, is true, which means root 2 is not a member of the rational numbers. Okay, another very fundamental proof is that of the infinity of primes. So the theorem states that there are infinitely many prime numbers. And it's an interesting one, this, when you think about it. You might think, well, at some point numbers get so huge that something must divide into them. Or you might think, well, there's no real reason, why should they stop? They go on as big as we want, so probably they're going to go on forever. But in the end, we have to prove it. There's no thinking it through with this sort of thing. We have to actually prove it. So, logic of contradiction again, we assume the opposite of what we're trying to prove. So what we do is we assume there are finitely many primes. That's obviously the opposite of there being infinitely many. And if there are finitely many, then we could list them. So we've got the first prime, the second prime, the third, all the way up to Pn, which is the biggest prime. and they're in order. So it says Pi is less than Pi plus 1. So P1 is less than P2, P2 is less than P3, and so on. And the funny P with an extra line is the set of primes, which is a similar notation to the Q and the Z you've already seen. Little pi is any of the P1, P2, P3s. Then A line B means that A is a factor of B. So we might say we could have 2 line 10. 2 is a factor of 10. Okay, so moving on with the proof, we now carry on with logical steps. We now construct a number, and big N is all these prime numbers multiplied together and then add 1. Okay, now we now say that if we divide this big N by any one of those prime numbers, then we'll get another integer. Notice, by the way, I haven't stated that N is an integer, but because N is made of loads of integers multiplied together plus 1, it will be an integer. So when we divide it by any one of those prime numbers, we're going to get an integer. So the part of n, which is p1 times p2 up to pn, when we divide that by pi, it's going to cancel, leaving us with an integer. But we're going to also have plus 1 divided by pi, because that still needs to be divided. Carrying on, we've either got the situation here n is a prime number, or n is not a prime number. Now let's have a look at each case. And this is going to lead us to our incorrect conclusions. Looking at n being a prime number, if n is a prime number, then we know that n is bigger than Pn, which is the one on our list, which is the biggest prime number, because n is made up of lots of primes multiplied together and then add 1. So it's got to be bigger than Pn, and that's a contradiction. N can't be bigger than Pn because we said at the top that there are finitely many primes, and we've put a list and Pn is the biggest one. So there's a contradiction. On the other hand, if we assume that n is not a member of the prime number, so n isn't prime, then there must be a prime number where p does divide into n, and that p must be bigger than the biggest one we've got on our list. The reason being that the statement in the middle where we said n over pi is m plus 1 over pi tells us that n cannot be divided by any of the prime numbers on our list. That leads us to the conclusion that if we say, okay, n can't be divided by any of the numbers on our list, so either it's prime, and that gives us a contradiction because it's bigger than the biggest prime on our list, or it's not a prime, but that gives us a contradiction because it would tell us that there is another prime that's not on our list and is bigger than Pn, and that's a contradiction too. So the conclusion contradicts reality, because what we've proven is that n cannot be a prime or not a prime, and it has to be one or the other, and that means because all our steps are logically correct, then the original assumption also contradicts reality and must be false. Therefore, the opposite of the original assumption, i.e. the theorem, is true, and therefore we can conclude that there are infinitely many primes.